So what's the link with the limit of a function? Intuitively, you think of limits of a sequence or a function at a point to be the value towards which the function gets close to as x gets closer to c. You say that the limit of the function f at x when x goes to c equal to L if you get something. But this picture here is really informed by our intuitive notion of functions as being continuous on calculus for sure. It's a little bit more complex than that. Let A be some subset of R, f a function which is defined from A to R. If C is a limit point, okay, it's important. L is going to be the limit of f. C, if for every epsilon greater than 0, you can find a corresponding delta epsilon greater than 0, such that distance between f at x and L can be made as small as you want whenever x is brought close enough to c. One thing we'll need to specify is that these values of x should stay within the domain of A, otherwise f at x might not be defined properly. If A is an interval, that's usually not a problem, but if A is some more exotic set, there might be some subtleties to it. But graphically, what does that mean? It means that if this is the function, the graph of the function, and this is the point that interests you, you've shown, first of all, that C is a limit point of the domain of the function, so things make sense. We can have sequences converges to C. We're saying we have a potential value L. You give me some epsilon. I can find a corresponding interval, in this case, let's say C plus delta epsilon, C minus delta epsilon, where all of the values of the function will be closer than epsilon, will be within epsilon of the candidate limit L. And if you give me a different epsilon, I feel like that's not the epsilon I want a different epsilon. If you give me a different epsilon, I might need to shrink my neighborhood of C, but I will be able to find a point where all of the values of f in that neighborhood are actually within epsilon of the value. So it's the same sort of game as before. It's the epsilon delta epsilon game. You give me an epsilon, or I give you an epsilon, and then you need to provide me with the delta epsilon, which will guarantee that the conditions are met. This case means that the function will be close enough to L. We write this mentioned here. The limit of x goes to c. F at x is L. That's our epsilon delta definition. Graphically, for a given epsilon, it's equivalent to putting a horizontal strip of width 2 epsilon around the line y equals L and showing that you can find a neighborhood V delta of the point of interest C such that f at x is in the strip for every x in the example. Consider the following function. It's a function from the semi-closed, semi-open interval 0, 1, and 2R. Takes on the following values. It is either going to be 2x within the interval 0, 1. It's going to be 3 if x is equal to 0. Show that the limit of this function, x goes to 0, is 2. And as was the case with the definition of the limit of a sequence, in order to be able to use the definition limit of a function, you need to have a candidate L. It needs to be given before you go and try to prove. Let's verify if this makes any sense. Point 0 here, point 1 which is in there. It is meant to be 2 everywhere except at this point. Now, does it make sense that the limit of this function should be 2? Well, as I get closer and closer to 0, I sort of see that I'm not moving, even though the value of the function at 2 is not equal to, even though the value of the function at 0 is not equal to 2, the limiting behavior is that it should be 2. Let's see if this makes sense. So let epsilon be some positive number. I'm going to pick for you a delta epsilon here. the delta epsilon would be 1, no matter what epsilon you pick. In general, that's not going to be the case. In general, that's not going to be the case. The delta epsilon you pick will depend on epsilon, but in this example, it doesn't explicitly depend on it. Then, whenever x is within delta epsilon away from the limit point 0, without being equal to 0, but that's taken care of by this statement here. In other words, whenever x in absolute value is smaller than 1, but all of these values here of x have to be positive. So whenever x is between 0 and 1, we have f at x minus L will be f at x minus, well, the candidate for L. And what's f at x? Well, if x is between 0 and 1, by definition, this is equal to 2. So 2 minus 2 equal to 0, and that's definitely smaller than epsilon because you picked epsilon to be greater than 0. So what's happened here? For any arbitrary epsilon greater than 0, I could find a delta epsilon, in this case 1, which was such that whenever 0 was smaller than x minus c in absolute value, which was smaller than delta epsilon, which translated to saying that 0 was smaller than x smaller than 1, the difference between the value of the function and the candidate for the limit, f at x minus L in absolute value, was in fact equal to 0, which was always smaller than x. And so the definition is satisfied. The limit of this function is 2. Alright, you'll agree with me that this isn't a completely interesting example. It doesn't really illustrate anything other than the fact that, well, this is how the definition works. Let's try to find something perhaps a little bit more, with a little bit more substance. So we'll look at the following function. Every x, it associates the number x squared plus 2, x plus 2, divided by, first we notice that this function is well defined. At no point am I dividing by 0. The rational function, this is the only place where things could be ill-defined. Dividing. Let's show that the limit of the function x goes to 2, L is c. Is it indeed the case that 2 is a limit point? The set A is, here's a function of values of A which converge to 2. So 2 is indeed the limit point of this interval, each of these points here being in a set of interest. Okay, so the question is well posed. It makes sense. Let's try to find. Let's see what the proof makes. So for an arbitrary epsilon, I'm going to set corresponding delta epsilon to be epsilon. Then, if I look at the distance between f at x minus L, which would be the distance between x squared plus 2x plus 2 divided by x plus 1 minus 10 over 3. This is going to be equal to, I'll let you work it out, 3x squared minus 4x minus 4 divided by 3x plus 3. And then you can factor this. The trick here is to try to find an expression in here which will contain x minus 2 in absolute value. Because in the definition of the limit, right, this is supposed to eventually be smaller than epsilon whenever x minus 2 is smaller than delta epsilon. So you need to find a way to rewrite this expression so that you have some function of x minus c. In this case, it's 2. Now, I claim that this is less than x minus 2. Is that the case? Well, 3x plus 2 is smaller than 3x plus 3 in general. And so the ratio of 3x plus 2 to 3x plus 3 should be smaller than 1. The only place where you might have a problem, potentially, is if you had negative numbers. But in order for 3x plus 2 to be negative, you would need values of x which are smaller than, what, 2/3? And your values of x tend toward 2. So there's going to be a point after which your x values are not going to be smaller than 2/3. In other words, if delta epsilon is small enough, which is to say that when epsilon is small enough, this thing here is never going to give you values of x smaller than 2/3. So this makes sense. Now, we would like for this to be smaller than epsilon. Well, if we know that x minus 2 is going to be smaller than delta epsilon, the best way to guarantee that x minus 2 is also smaller than epsilon is to set delta epsilon to equal the epsilon. This is how we found this number here. So it's not technically true that it has to work for every single value of epsilon. It's just got to work for some threshold epsilon and in all of the smaller values. Okay, let's do one more example. F is going to be defined on the reals except for 0. Every value in the domain of the function will go to x squared cosine of 1 over. Good luck trying to draw this. Show that limit f at x when x goes to 0 is 0. Now the function isn't defined at 0, right? You have x squared, 0 squared times a cosine of 1 over 0, and that's just not defined. And we show that the limit is 0 nonetheless. Does it make sense to ask this function? X is going to 0, but the function is not defined at 0. It only makes sense if 0, the limit point of the domain. It is. The sequence 1 over n converges to 0, and 1 over n is actually in the reals minus 0 for every n. So 0 is a limit point of the set R minus 0, and so this question is well posed, even though the function is not defined at 0. We just now prove the statement. Let epsilon be greater than 0. I'm going to pick delta epsilon to be the square root of epsilon, also greater than 0. Then, whenever 0 is greater than x minus c, which in this case is 0, which is smaller than delta epsilon, which in this case we told you was going to be the square root of epsilon, we have f at x minus l, which is going to be x squared times the cosine of 1 over x minus potential value l is 0, the candidate value of l, you could say, which is 0. Here, I should also mention that we want the x's to be in the domain. It is automatically going to be the case by the way this is written, but we need to specify. There'll be instances where this will not automatically give us that x is in the domain. So this is going to be, this difference is going to be the norm of x squared times the cosine of 1 over x. And norm, and this, by definition, always going to be smaller than or equal to the square of the norm, because the cosine is always between minus 1 and 1, no matter what argument you give it. So the absolute value of the cosine is smaller than or equal to 1. Now we haven't formally proven this here. This is something you have to prove, but let's take it for granted for this point. Okay, I'm left with the norm of x squared. It's not quite what I wanted, at least not at first glance, but remember here, when we're saying that 0 is smaller than x minus 0 in absolute value, what we're really saying, here's your norm, really x minus. It's going to be smaller than delta squared. Square on both sides, and both of these quantities are positive. And if I've set it up so that delta epsilon was the square root of epsilon, this is actually going to be equal to epsilon. Proven. Of course, how did I find my delta epsilon to be smaller than the square root of epsilon? I first worked through this, found a way to rewrite fx minus L using inequalities that would involve what my x minus c would look like, and afterwards I just solved for delta epsilon. But again, shown that the limit of this funky function when x goes to 0 is in fact 0. As was the case with sequences, if a function has a limit at a given limit point, the function admits a limit point, then it has at most one limit. It cannot have multiple. A sum let if a function from A to R, C is a limit point of A, then F has at most one limit C. And we prove this uniqueness result the same way we always prove uniqueness result. We're going to assume that there are two limits, and we'll show that they have to be the same. Let these limits here be L prime and L prime prime, and we're going to assume they're not the same. One of them is smaller than the other. In that case, without loss of generality, let it be L prime, which is smaller than. So if L prime is smaller than L prime prime, and the following quantity, which I'm going to call epsilon, is greater than 0. By the definition of the limit, you're going to be able to find a delta epsilon prime and a delta epsilon prime prime, one for each of L prime and L prime prime, such that fx minus L prime will have to be smaller than epsilon, so value, whenever x minus c is smaller than delta epsilon in absolute value, and x is never and x is not equal to c, and x belongs to the domain of the function a, and the same thing for the other limit. I'm going to pick the delta epsilon, which is the smallest one of these two. And now this holds, and this holds whenever x minus c is not equal to 0, and then absolute value is smaller than delta epsilon, and x. When that's the case, then what we will find is that f at x on the one hand will be smaller than L prime plus epsilon, because f at x minus L prime is smaller than epsilon. Then it's going to be L prime plus, well, we know what epsilon is in this specific case. We've set it to be L prime prime minus L prime divided by 3. Let me rewrite this here. This will be 2L prime plus L prime prime divided by 3, which I can also rewrite as L prime plus L prime prime divided by 3 plus L prime over 3. And that's going to be smaller than L prime plus L prime prime divided by 3 plus L prime prime divided by 3. Because we've assumed, you remember, that L prime is smaller than L prime. And then you can rewrite these terms as twice L prime prime plus L prime divided by 3, which is the same as L prime prime minus L prime prime minus L prime divided by 3. Just rearranging the terms. That's L prime prime minus epsilon, because this was our value of epsilon, which will be less than x, which is a contradiction, because this means that f at x is smaller than f at x, and that's impossible. The inequalities here are strict. So if we assume that L prime and L prime prime take on different values, that one of them is smaller than the other, we get a contradiction. That means that L prime cannot be smaller than L prime prime. Look, we picked L prime as being smaller than L prime prime just to have something to work with. If they're different, it's the other one, L prime prime, which is smaller than L prime. Just go through the exact same exercise and you'll get the same contradiction. You have no choice but to have that L prime is equal to L. The function has a limit at a given point and has at most, well, I keep on saying this. What I'm really saying is that if it has a limit, it has exactly one. Or a function has at most one limit at a given. But as was the case sequences, I know I've mentioned this before, if you do not have a candidate for the limit, this definition is completely useless. You need to have an L in mind to show that the limit of the function is indeed L.